Welcome to Math TV with Professor V. This is the final exam review, part 4 for Calculus 2, and we're going to focus on sequences and series for the duration of the video. And I know most of you guys have already finished your finals, but not everyone has, and I had a request from a subscriber to get this out, so here we are. Now, I'm going to just do a quick recap of pretty much all the topics in this unit. If you need more in-depth explanations, examples, etc., all of the video lectures are linked in the description box, so you can just go click there and browse around to fill in any extra review that you might need, okay? So to kick things off, we're going to talk about sequences first, and a sequence is just an ordered list of terms. And we say that a sequence, usually we refer to it as a sub n. It has the limit L if the limit as n approaches infinity of a sub n equals L. And we say a sequence is convergent as long as this limit exists as a finite number, okay? A sequence is divergent if this limit doesn't exist or if it ends up being positive or negative infinity. So when you're asked to determine the convergence of a sequence, not a series, we're not talking about series yet, just a sequence, you take the limit as n goes to infinity, all right? And if you get a number, then it converges. That's the big thing. Okay, so here's just a little summary. When you're looking at a sequence, if you have r raised to the n power pop up in there, check as long as r is between -1 and 1, then that will be convergent. If r is less than 1, the absolute value of r, then as n goes to infinity, this is going to go to 0. Sometimes you might need to use the squeeze theorem if you see sines or cosines pop up. Not always, but sometimes. If you have a ratio like so where an and bn are polynomials, you can divide by the highest degree of the denominator. If you want to do L'Hopital's rule, you got to change it to f of x. Don't do L'Hopital's rule with n's in it. I'll talk about more why. An increasing sequence is a sequence whose terms keep getting bigger and bigger. Decreasing, they get smaller and smaller. We'll look at that in a little bit. If you have a sequence that's either increasing or decreasing, it's called monotonic. A sequence that's bounded above is when there's some number h such that all the terms are less than or equal to that. A sequence is bounded below if there's a number, we're calling it lowercase m, such that all the terms of the sequence are bigger or equal to m. If you have bounded above and bounded below, then you have a bounded sequence. And then we have this snazzy little theorem that every bounded monotonic sequence converges. That's a ton of info, so now let's work through some examples so you can see how to put all this to use. But hey, take a screenshot while this is here. Good? Okay. So here, we're asked to find the limit of the sequence if it converges, otherwise indicate divergence. And here we're going to utilize this fact that the limit as n goes to infinity of r raised to the n equals 0 if r is between -1 and 1. And as a note, if r is equal to 1, then the limit as n approaches infinity of r to the n is 1, so that converges also. So here, this example, this 0.1, that's your r. And that's for sure between -1 and 1. So if I take the limit as n approaches infinity of an, which is 3 plus 0.1 to the n, this whole term here is going to go to 0 based on this fact, okay? And that should make sense because 0.1 is a fraction, right? It's less than 1, 1/10. If you keep multiplying something by 1/10 over and over and over, right, it's going to get smaller, 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 go to 0. So the limit here is just 3 plus 0, which is 3, and that's a finite number. So therefore, we can say the sequence converges. They didn't ask, but converges. Let's write that down. AN converges. Okay. Here's another example. AN equals 2 minus 1n, you don't need to put the 1, plus 3n to the 4th over 5n to the 4th minus 2n cubed plus 2. So again, they're asking us, does the sequence converge or diverge? You have to remember that means take the limit as n goes to infinity, always to infinity. So here's the terms, 2 minus n plus 3n to the 4th over 5n to the 4th minus 2n cubed plus 2. You could try L'Hopital's rule, but you have to change it to a function, f of x. So I don't want to do that. I'm just going to divide by the highest power of n in the denominator, which is n to the fourth. So I'm going to divide everybody by n to the fourth. All right. And then let's see, what do we have? So we've got the limit, n goes to infinity, 2 over n to the fourth minus 1 over n cubed plus 3. That's my numerator. And then in the denominator, we're going to have 5 minus 2 over n plus 2 over n to the fourth. Okay, this limit should be pretty straightforward. As n goes to infinity, 2 over n to the fourth goes to 0. 1 over n cubed goes to 0. This negative 2 over n goes to 0. And so does 2 over n to the fourth. So all I'm left with is a 3 in the numerator plus zeros, and then a 5 in the denominator and some zeros. So this limit is 3 over 5. Now, when you're dealing with a sequence and figuring out whether it converges or diverges, you don't care like what this limit is. As long as it's a finite number, then we can say an converges. It doesn't even matter. If it's 1,000,001, it's still convergent, okay? As long as it's a finite number, we're good. This is for sequences. Okay, now here's a little spicy one. Again, remember, you always take the limit as n goes to infinity, and then we have 1 plus 8 over n raised to the n. Now here's the thing that's going on. As n goes to infinity, this 8 over n, that's going to 0. So the base is approaching 1. And then n again is going to infinity. So the exponent is approaching infinity. So you basically have 1 to the infinity. That's an indeterminate form, indeterminate power. And the way we deal with indeterminate powers is we have to use L'Hopital's rule. I'm sorry, there's no way around it. And you have to bust out that extra natural log. So you can move the exponent to the front. If you forgot, don't worry, I'm going to work through this one step by step, but you should have seen it in Calc 1 and practiced quite a bit. So here's the big deal though. You can only use L'Hopital's rule on differentiable functions, and a sequence is definitely not differentiable. Okay, it's not continuous. So no chance. So what we're going to do is instead say, all right, let f of x equal, and then now just replace all of the n's with x's, okay, in the original sequence. So I'm going to call f of x 1 plus 8 over x to the x. And I'm going to find the limit as x goes to infinity using a function of x instead, because now it's differentiable, okay? Now, I'm going to call this, I don't know, y, same thing as f of x. ln of y is going to be ln of 1 plus 8 over x to the x. Where's the ln coming from? Because I know I'm going to need to move this exponent to the front. And only log properties let me do that. So I have x times ln 1 plus 8 over x. And remember, to use L'Hopital's rule, we need a quotient. So I want to rewrite this as ln of 1 plus 8 over x over 1 over x. This is an old trick. Okay, so then now we're going to take the limit as x goes to infinity of ln of y. So that's the limit as x goes to infinity of what I have up above, ln of 1 plus 8 over x over 1 over x. Oop, I don't want to type. Okay. Now remember, you can only use L'Hopital's rule on two indeterminate forms, 0 over 0 or infinity over infinity. And in this case, let's see what we got. If x goes to infinity, 8 over x is going to 0. So then we just have natural log of 1, which is 0. So numerator is going to 0. X is going to infinity, so 1 over x is also going to 0. So we have 0 over 0. Fabulous. That means we can apply L'Hopital's rule. If you try applying it when you're not supposed to, it'll come out wrong. I know. Okay, so here we go. Limit x goes to infinity. When we use L'Hopital's rule, you take the derivative of the numerator and then the derivative of the denominator separately. Don't do quotient rule. Okay, derivative of the numerator. We have natural log of something. So derivative of natural log of something is 1 over the something. And then by the chain rule, I have to multiply by the derivative of the something, of what's inside. So derivative of 1 is 0. Derivative of 8 over x. Don't you dare do the quotient rule. No, no, no. 8 over x is 8x to the negative first, right? Okay, so the derivative would be negative 8 over x squared. See? Only do quotient rule if you have variables in the numerator and variables in the denominator. If you just have a constant in the top, you don't need to do quotient rule. Good. Now, derivative of the denominator, that's x to the negative first, so the derivative is going to be negative 1 over x squared. Okay. Oh, this is nice. Look at this. Look at this. These negatives cancel. In fact, these x squareds cancel. Okay, so now all I have is limit x goes to infinity of 8 over 1 plus 8 over x. And then if x goes to infinity, 8 over x is going to 0. So I'm just left with 8 over 1, which is 8. All right, so let's summarize. Oh my, I need more paper. Okay, now let's summarize what we just found, okay? This tells me now that the limit as x goes to infinity of f of x is going to be e raised to the limit as x goes to infinity of the natural log of f of x. Because this is the limit that we just found, right? We added in the extra natural log. So if I take e and raise it to all of this, then it's basically, you know, going to undo each other, get rid of the natural log, and I'll have the original limit that I'm looking for. So this is going to be e raised to the 8th. That's the limit as x approaches infinity of f of x. And then, following that same logic, that means the limit as n approaches infinity of the sequence 1 plus 8 over n to the n is also equal to e to the 8th. Okay, and you do need to write it out like this. So I would say the most common thing students forget about is needing to switch to a function. And then also when you have an indeterminate power, you need to apply natural log so you can move the exponent to the front. This infinity needs to get moved to the front here, and then you have to make a quotient. Okay, if you need to review L'Hopital's rule in indeterminate forms, I have a video on that. I'll link it here. Okay, good. That's just a special case I wanted to work through. If you're like in crunch time for your final, I would say maybe just let it go. Okay, determine if the sequence is monotonic and if it is bounded. Okay, so first let's check for, is it monotonic? So monotonic means it's either always increasing or always decreasing. So you want to compare an plus 1 and an. And if you can say that this is bigger or equal to an, then it's increasing. That means the terms get bigger. Or if you can say that an plus 1 is always less than or equal to an, then it's decreasing. So let's see here. An plus 1 would be 5 times n plus 1 over n plus 1 plus 1. So what's that? 5n plus 6 over n plus 2. And then if I compare that with an, which is 5n plus 1 over n plus 1, it's not obvious that one is always bigger than the other. Like notice here, this denominator got a little bit bigger. When denominators get bigger, it makes the whole thing smaller. But then the numerator got bigger at the same time. So it's not obvious. If only one quantity was changing, only the numerator or only the denominator, then we could tell for sure, oh, an plus 1 is bigger or smaller or whatever. But in this case, it's ambiguous, right? And don't plug in n equals 1, 2, 3, 4, and then think like by observing finitely many, you see a pattern, okay? You could list out the first million terms, and even if it looks like they're increasing, You don't know that term 1,000,003 won't decrease. So you can't just list out terms in math and think like, oh, I showed it. All right, that's never good. That's not okay. So if an inequality is not going to work, then your other option is you could look at the difference. You could do an plus 1 minus an, see if you could play around with that. Or, my favorite, I like to take a derivative. Because we know derivatives, the sign of the derivative tells us if a function is increasing or decreasing. But again, we need a function to take a derivative. So I'm going to make one. I'm going to say let f of x equal 5x plus 1 over x plus 1. And I want to look at f prime of x. Okay, let's do it. So f prime of x, now we use quotient rule. So low d high, denominator times derivative of numerator, minus high d low over low low. Okay, let's clean this up. This is going to be 5x plus 5 minus 5x minus 1 over x plus 1 squared. Ooh, this is nice because look, these 5x's cancel. And then all I'm left with in the top is a 4 over x plus 1 squared. And I can tell, okay, no matter what I plug in for x, this is always greater than 0. Right? As long as x isn't -1, which would make it undefined. I'll say it's greater than 0 for all x's greater than or equal to 1. Because usually we start our sequences at 1 anyways. So what does that tell me? If the derivative is positive, that means f of x is increasing. So an, which equals 5n plus 1 over n plus 1 is monotonic, increasing also. Fabulous. Now, the other thing it asks us to determine is if the sequence is bounded. Is it bounded? Okay. Well, since it's increasing, that means the first term, a1, is a lower bound, right? Because every term after that is going to be bigger, so the first term can act as a lower bound. So what's a1? a1 would be 5 times 1 plus 1 over 1 plus 1, so that's 6 over 2, so this is 3. That's my lower bound. Is there an upper bound, or as n goes to infinity, does an approach infinity? Well, I don't know. So once you know a sequence is monotonic, you already have one of the bounds, okay? So since this one's increasing, the first term is the lower bound. If it had been decreasing, the first term would be an upper bound. To check if you have now a bound on the other side, you always should take the limit as n goes to infinity. So you're going to take the limit as n goes to infinity of an, because I want to know, does it blow up or does it level off? Yeah? Again, I'm not going to do L'Hopital's rule because then I have to change it to f of x, so I'm just going to multiply by 1 over n. And then here we have limit n goes to infinity, 5 plus 1 over n over 1 plus 1 over n, and then this goes to 0, this goes to 0, so this is just 5 over 1, which is 5. Oh, so that's my upper bound right there. That means the sequence does not increase with no limit, yeah? We know it's increasing, but it's going to level off. So that means, yes, it's bounded and it's monotonic. So by our theorem, that means an converges. It's a convergent sequence. Every monotonic bounded sequence is convergent. If you want more info on that, I have a whole video on monotonic and bounded sequences. My goodness. Okay, but I would say, final exam, we're crash studying or whatnot. I don't know what you kids call it these days, but I think that's enough. Okay, now let's get into series. That's all we talk about sequences. First kind I want to talk about are telescoping. Telescoping series are when you find S sub n, the nth partial sum, and you list out the first few terms and the last few terms until you see a pattern, and a bunch of stuff in the middle is going to cancel. That's why it's telescoping, because it can collapse, like when you take a telescope and collapse it. When you take the limit as n goes to infinity of S sub n, if you get a finite number S, that's actually the sum of the series. And its sum is S. And then if the limit of the partial sums goes to positive or negative infinity or doesn't exist, then the series diverges. And I should mention, like, the transition from sequences to series is that you take the terms of your sequence, A1, A2, and now instead of separating them with commas, we add them together, and that's what makes a series. If you only add up n many terms, then that's the nth partial sum. If you go for infinitely many, then you have an infinite series, okay? You should know all this, so let's just jump right into it. Determine if the series converges or diverges. If the series converges, find its sum. So I would say, like, the number one thing students tell me they have a hard time with is, how do I know if it's going to be telescoping? Like, how do I know to take that approach instead of one of the many tests that we learn in this unit? And I think the biggest clue is in the directions. When you're reading the directions, it'll usually say, figure out if it converges or diverges. That's nothing new. The fact that it says find the sum, ooh, we don't do that often. The only time you can find the sum of a series is if it's geometric, if it's telescoping, or if it's a Taylor or Maclaurin series. Actually just Maclaurin, but whatever. Maclaurin is a special case of Taylor. So the fact that the directions tell me to find its sum means it has to be either geometric, telescoping, or Taylor-Maclaurin. And I'm looking at it, this is not geometric. We'll talk about geometric in a hot second. Not Taylor or Maclaurin, so it's got to be telescoping, okay? So just remember that fact, because the directions give you so many clues. So now what I'm going to do is figure out an expression for the nth partial sum. Okay, so S sub n is going to be the sum I equals 1 to n of 1 over, now change all those n's to i's. So rad I plus 1 minus 1 over rad I plus 2, like that. Now, starting at I equals 1, you're going to list out, like, the first few terms until you see a pattern, okay? So if I is equal to 1, I'm going to have 1 over rad 2 minus 1 over rad 3. That's for I equals 1. If I is 2, we'll have 1 over rad 3 minus 1 over rad 4. I know that's 2, but I'm not going to simplify just so I can see a pattern, you know? Now I equals 3. 1 over rad 4 minus 1 over rad 5. Do you see a pattern? I feel pretty confident, right? Like, these terms cancel. These terms cancel. I know the 1 over rad 5 is going to cancel with the next term. So I'm just going to put dot, dot, dot. And then now the last term is going to be the nth term. So the nth term, I'll just list it here. It would be 1 over rad n plus 1 minus 1 over rad n plus 2. That's for I equals n. What comes before? What's before n? N minus 1. I equals n minus 1. So that would be 1 over rad n minus 1 plus 1 is just rad n minus 1 over, this would be rad n plus 1. What comes before n minus 1? Good, n minus 2. So this would be 1 over n minus 2 plus 1, rad n minus 1. And then rad n minus 2 plus 2, just rad n. I think I see enough of a pattern. Do you? See, this cancels. Look at this little telescope collapsing in front of our eyes. You know what? This was a minus. Whoops-a-daisy. Otherwise it wouldn't collapse, huh? We'd be in deep trouble. Okay, and then this would cancel had I written more, okay? Here's also another big helpful fact. However many terms don't cancel in the beginning will match the number of terms that don't cancel at the end. So what do I mean by that? If you have like one little survivor here, you will have one survivor at the end. If I had like 2 terms that didn't cancel in the front, 2 terms shouldn't cancel at the end. I have a whole video on telescoping series too, if you need more. Okay, so that means Sn reduces to 1 over rad 2 minus 1 over rad n plus 2. Now what do we do with this? We take the limit as n goes to infinity of Sn. And if we get a finite number, that's the sum of the series. How cool. So as n goes to infinity, 1 over rad 2, that's just a constant. And then this 1 over rad n plus 2 is going to go to 0. So woohoo! We have a constant, that's the sum, and the series converges. We didn't use a test. This is literally just the definition of a convergent series, infinite series, okay? Usually when you apply one of the tests that you learn later in the unit, you have to say like which test you used, okay? In this case, it's just the definition, but check with your instructor what they want, okay? Good. Now we talked a little bit earlier about geometric series being another kind of special series whose sum we can actually find. All right. So geometric series have the following form, sum n equals 1 to infinity. I mean, sometimes they'll start at 0, okay? And then you can have a constant times r, which is the common ratio, raised to the n minus 1, or it could be to the n, it just depends. It converges so long as absolute value of r is less than 1. And the formula for the sum is you take the first term divided by 1 minus r, and then it diverges if r is greater than or equal to 1. Okay? Good. So here it says find the sum of the series. So I can tell it's geometric. It doesn't look like it's going to be telescoping, and it's definitely not a Maclaurin series. So this is AN right here. I want to figure out what R is, but oh me, oh my, it looks like a hot mess. So let's clean things up. So AN is negative 1 to the n minus 1 times 9 over 7 to the n. Just keep in mind here, R is everything that's being raised to the n. It doesn't have to have a minus 1 in it, okay, whatever. So let's see if we can identify everything that's being raised to the nth power. This is negative 1 to the n times negative 1 to the negative first, right? Good. Times 9 is not raised to the n over 7 to the n. So this is raised to the n, this is raised to the n. Let's put them together. You see what I'm doing? So I have negative 1/7 to the n. And then I have negative 1 to the negative first. That's just negative 1 times 9. So I've got negative 9. So this is kind of like the C in the formula up above. And then this is my R. All right. So R equals negative 1/7. And absolute value of R is 1/7, which is less than 1, which means this series converges. So the formula for the sum is the first term. I'm going to put A1, but it's just the first term. If this started at 0, you would put A0 here, okay? Over 1 minus R, and R is negative 1/7. Okay, so A1, the first term, let's see. I'm just going to plug in 1 for n here. It's going to be negative 9 times negative 1/7 to the first. So that's just 9 over 7. So we've got 9 over 7 over 1 plus 1 over 7. That's 7 over 7 plus 1 over 7. So that's 8 over 7. And then the 7's cancel out, and this is just 9/8. All right. Depending on where you studied pre-calc, you should have seen some exposure a little bit to geometric series and sequences. Yeah. So hopefully this is review. If not, it's not too crazy, right? Okay, good. That's all I'm going to say about geometric. Now, one other test that is useful is the test for divergence. Keep in mind what the name of this test is. It is the test for divergence. Therefore, it can only be used to tell you that a series diverges. It cannot be used to tell you that a series converges. Remember the name. Don't use it inappropriately. So what the test for divergence says is, if the limit as n goes to infinity of an, so if the terms of your series don't go to 0 or it doesn't exist, then the series is divergent. If the terms go to 0, you have no info. The series could still converge or diverge. So this test only works if the terms don't go to 0, and then you can say the series diverges. It will never help you say that a series converges, okay? Great. So on that note, let's look here. Determine if the series converges or diverges. If it converges, find its sum. Oh, that tells me it's going to be either geometric, telescoping, or Maclaurin. This is none of those. So probably we're not going to be able to find the sum. All right. An is natural log of 4 over n. So I'm going to check where are the terms going. What is the limit as n goes to infinity of ln 4 over n? Well, 4 over n approaches 0. And so you could think of the graph of natural log. We know that its domain is from 0 to infinity. And so you can only approach 0 from the right, which is fine because n is going to positive infinity. So you can just imagine that vertical asymptote. So natural log, as the argument gets closer and closer to 0, is approaching negative infinity. Okay, and I'm just doing this based on imagining the graph. If my students always forget the graph, that's fine. I mean, it's not fine, but what are we going to do? So your other option to do this limit is you use your log properties, and you can write this as natural log of 4 minus natural log of n, yeah? And for some reason, I don't know, they like doing it this way better. As n goes to infinity, natural log of n is going to go to infinity, yeah? Do you remember the graph just a wee bit? Please pretend that you do. It goes through 1, 0, like that, and it goes like this. This is ln of x, okay? So yeah, as n goes to infinity, ln goes to infinity. So you have a number minus infinity, and so this limit is negative infinity. Either way you think about it, negative infinity is the result. That's the limit of the terms. And last time I checked, negative infinity is definitely not 0, which means that this series diverges by the test for divergence. Okay. What if the terms had gone to 0? Then I have no information. Then I need to use a different test from later in the unit. Okay? Good. Let's look here. Again, they're asking, does it converge, diverge? And if it converges, find the sum. So now my brain's going like, ooh, is it geometric or telescoping or Maclaurin? If you try doing the test for divergence, it's inconclusive. Because look, if you do the limit as n goes to infinity, 1 over 8 to the n minus 1 over 6 to the n, both the denominators are getting very, very big, right? So this goes to 0, this goes to 0. So this limit is 0, which means we have no info. I don't know if it converges or diverges. It could do either. But I am noticing these both look geometric. Now, the tricky thing is there's subtraction here. You're not allowed to distribute a sum, an infinite sum, unless you know that they're both convergent. So we're going to consider them separately. Okay, consider first the sum n equals 1 to infinity of 1 over 8 to the n. Now 1 over 8 to the n is the same as 1/8 to the n, right? Because 1 to the n is just 1. So this guy's geometric. R is equal to 1/8, and the absolute value of r is less than 1, so it's going to converge. I'll write that down. And so let's figure out the sum here. I'll call this S1 because this is the sum of the first little series. The first sum is going to be A1. So if I plug in 1 for n, that's going to be 1/8 over 1 minus r, 1 minus 1/8. So that's 1/8 over 7/8. So this is 1/7. Okay. Now let's consider the other guy. The sum, n equals 1 to infinity, 1 over 6 to the n. Again, 1 over 6 to the n, that's the same as 1/6 to the n. This is geometric too. Fabulous. R is 1/6. Absolute value of r is less than 1, so yeah, this guy converges also. And this, the sum of this second little series here, A1 would be 1/6 to the first, so that's 1/6 over 1 minus 1/6. So that's 1/6 over 6 over 6 minus 1 over 6, 5 over 6. So this is 1/5, yes? Okay. Great. So they both converge, which means that the original series converges also. If one of these guys was divergent, then the whole thing would be divergent. Okay? But we're in good shape. So the overall sum of the original is going to be the difference, S1 minus S2. I'll write it out nicely. So that means the sum, n equals 1 to infinity, 1 over 8n minus 1 over 6 to the n is going to be S1 minus S2. So 1/7 minus 1/5, which is negative 2 over 35. All right, beautiful. I feel good about the geometric, telescoping, and test for divergence. So now let's get into the other tests that we can use. Integral test. What are the conditions of the integral test? When can we use it? Well, you have some sort of infinite series. You call an f of x instead, and f of x needs to be continuous, positive, and decreasing on 1 to infinity. And if that's the case, then the sum n equals 1 to infinity of an is convergent if and only if the improper integral from 1 to infinity of f of x dx is convergent. So basically, if the improper integral is convergent, then the infinite series is convergent, and then also if the improper integral is divergent, then the infinite series is divergent. So you do need to remember how to do your improper integrals. Let's work through an example right now. It says use the integral test to determine whether the series converges or diverges. Now, I know they told us to use the integral test, but you should always check that the conditions are satisfied, that they apply. So let's go ahead and just double check right now, okay? So the function f of x would be 5x over x squared plus 2. So let's check the three conditions. Is f of x continuous on 1 to infinity? Well, what kind of a function is f of x? F is a rational function. So if I know its domain, it's continuous on its domain. And rational functions, the only thing I'm worried is that the denominator can't be 0. And x squared plus 2 is never going to be 0. So the domain is all real numbers. So therefore, it's continuous on all real numbers, and it's going to be continuous on the subset from 1 to infinity. Is f of x positive on 1 to infinity? So yeah, look, the denominator is always going to be positive, and if we're only plugging in numbers from 1 to infinity, the numerator is going to be positive, so we're good. And then the last thing we have to check is decreasing. So you can use an inequality or just take the derivative. So let's take the derivative. Again, we need quotient rule. Do you remember when you were in Calc 1 and you learned the quotient rule and that's all there was to the problem? And now it's just like a little sidebar in a long problem. What does that tell you? Don't complain that your math classes are hard because it's just going to build. So one day you'll look back and wish you were doing this. Okay, Or maybe you're going to take some other class later on and it's not going to be straightforward and you're like, oh, math wasn't so bad. At least it was very procedural. Now I'm just struggling in some bizarre class. All right. Anyways, back to business. So this is going to be 5x squared plus 10 minus 10x squared over x squared plus 2 squared. So what do we have up top? Negative 5x squared plus 10 over x squared plus 2 squared. So I know the denominator is always positive. The numerator, though, hold up. I'm only interested on the interval from 1 to infinity. Now, if I plug in 1 for x, the denominator is positive, the numerator is positive, which would mean f prime is positive, so the function's increasing. Ooh, that's not good. What if I plug in 2 for x? That would make that 4 times negative 5, negative 20 plus 10. Now it's negative 3, 4, 5, etc. So the derivative is less than 0 for all x's that are greater than or equal to 2. Not 1 to infinity, 2 to infinity. And that's okay. That's good enough. So I wanted you guys to see an example where it's like, ooh, it's not increasing all the time, but it's eventually decreasing. Why did I say increasing? It's eventually decreasing, right? Just for a hot second, it increases and then it starts decreasing. So that's good enough. That is good enough for us. Okay. Great. So we can use the integral test. So now we're going to consider the improper integral from 1 to infinity of, where's my function? 5x over x squared plus 2 dx. And then hopefully you remember improper integrals. You learned them this semester. First thing, replace the infinity with a t, and we're going to take the limit as t goes to infinity now. 1 to t, 5x over x squared plus 2 dx. And then how would you evaluate this integral? Why, yes, a u sub. Maybe you can do it in your head. If not, write it out. So if u is x squared plus 2, du would be 2x dx. So 1/2 du is x dx. And here's my x dx. Okay. So we've got now the limit as t goes to infinity. Instead of 1 to t, let's see what our new limits are. So u of 1 is 1 squared plus 2, so that's 3. And then u of t would be t squared plus 2, and that's what you write. And then this 5 is going to go outside. Okay, here I am. And then x dx, this kidney bean, x dx, that's my 1/2 du. Well, guess where the 1/2's going? Outside with the 5 to keep him company. And then you're just going to have 1 over u. Okay, you know antiderivative of 1 over u, don't you? Yes, we do, Professor V. Limit t goes to infinity, 5/2 ln absolute value of u, evaluated from t squared plus 2 to 3. Leave the 5/2 out of it, okay? Constants are not invited to the party. 5/2 times ln absolute value t squared plus 2 minus ln, I don't need absolute value, 3 is positive. So let's see what's happening. T is going to infinity, so t squared plus 2 is going to infinity. We just looked at the graph of ln, didn't we? So if the argument's going to infinity, all of this is going to infinity. This is just a number. Infinity minus a number still goes to infinity, right? What about the 5/2? Nobody cares. 5/2 times infinity still goes to infinity. That's not doing anything. Okay, so this limit is infinity. Bum-ba-da-dum. What does that mean? That means the improper integral diverges. Ooh, so what does that tell me? That the sum, our OG infinite series, n equals 1 to infinity, of 5n over n squared plus 2 also diverges by the integral test. Okay, and I'm only going to do one integral test. Otherwise, this video would be 8 hours long if I did everything to cover every scenario. But the other thing that could happen is, instead of getting infinity or negative infinity, you get a finite number. That tells you then that the integral converges, so the infinite series also converges. I want to make something very clear. If this is a finite number, that is not the sum of the series. It will just tell you that it converges, but you do not know what the sum is. Okay? Okay. Now, using the integral test, we can prove that a special type of series converges or diverges, and that's the p-series. So p-series has the following form. It has to start at 1 or later, but not at 0, because it has the form 1 over n to the p. So I'm saying the problem is if n is 0, then this is undefined, okay? So we don't start there. It's 1 or later, and then you have n to the p. If p is between 0 and 1 inclusive, this series diverges. We know this from the integral test. If p is greater than 1, it converges. And if p is exactly equal to 1, it's called the harmonic series, and it falls under this case here where it diverges. You know, it's just so famous. It has its own name, that p-series. Look at it with its own name. P equals 1 is called the harmonic series, which is divergent, okay? Put those to memory. You don't need to prove them. If one pops up, you could just say this is a p-series. P is whatever, 5, 2, 1/3. Therefore, it converges or diverges, okay? Good. Now, why did I talk about p-series? Because we use them a lot when we do the comparison test. Comparison test, the most popular series to compare your series to are p-series or geometric series. So to do the comparison test, you have some given series, and then you're going to compare it to some other known series, usually geometric or p-series, that you can say it already converges or diverges. Here are the conditions. If the terms of an are less than or equal to bn for all n, and you know bn converges, then an has to also converge, because basically the terms of an are less than the terms of another convergent series. If an is greater than bn, and you know the sum of bn diverges, then the sum of an also diverges. Now this is the direct comparison test. Students don't like this one because if you don't show the correct direction for the inequality, then the test cannot be used, okay? We're going to talk about limit comparison test in a hot second, and you don't have to show an inequality, so that's really like a fan favorite. And in my class, I don't care. Like I'll never force you to do direct comparison versus limit comparison. So I'm just like, learn whichever one you want to learn and use it. But depending on your teacher, I don't know what's going on. So we'll do a direct comparison test. They don't usually say the word direct, but the other test is limit comparison test. So determine if the series converges or diverges. You kind of already have to know before you start whether you think it's going to converge or diverge, so you can show the correct inequality. So here's the deal. I'm looking at the numerator. 5 is a constant. 6 times cosine n. Does cosine n do anything spicy? Let's think. If n goes to infinity, well, we know the graph of cosine. It's just this wiggly little guy, right? So it's not going to go to infinity or negative infinity. It's just wiggling all around the place. Okay, so this is, not doing too much. Ooh, in the bottom, I see n squared. I see n squared. And I know the sum, n equals 1 to infinity, of 1 over n squared is a p-series. P equals 2, which is greater than 1. So this p-series converges. So I have a feeling like this will converge also. And if I'm going to use the comparison test, then basically bn is this 1 over n squared, and I need to somehow show that an is less than or equal to bn. And I can't do that because this is for sure bigger than 1. So you're going to be a little clever, like a little weasel, and you go, how can I say 5 plus 6 cosine n over n squared is smaller than this p-series? Well, I know cosine is bounded between -1 and 1. So this is less than or equal to 5 plus 6 times 1 over n squared, right? Which is 11 over n squared. So I'm just going to slap an 11 here. And you might be like, that feels very illegal. No, it's not. Think about it. If you have an infinite series and you multiply by a constant, if it converges, it's still going to converge. If it diverges, it's still going to diverge. Okay? We have a theorem that tells us we're allowed to do this. So manipulate appropriately so you can use the comparison test. I'm actually done, right? I just showed this is an, and now I'm actually calling this bn, not just 1 over n squared, okay? And we're done. So therefore, the sum, n equals 1 to infinity, 5 plus 6 cosine n over n squared also converges by comparison. And it all hinges on the fact that cosine of n has to be less than or equal to 1. Okay? If that wasn't there, if it was just, a number, that's fine too. But then you wouldn't even need a test. You could just say it's a multiple of a p-series and move on with your life. Okay, that's all I'm going to talk about comparison test. I have a whole extra video on it. Let's get to limit comparison. That's more loved and useful, I think. So suppose an and bn, the sum of an and the sum of bn are series, and they have positive terms. If the limit as n goes to infinity of an over bn equals c, which is a positive constant, then both series converge or both series diverge. So the cool thing is you don't have to show an inequality. Ooh. And then as long as your limit is a finite number, not 0, so positive constant, then you know both series basically behave the same. If you compared it, if you took the ratio of your series with something else that is convergent, then your series converges also, or if it's divergent, then your series diverges also. So I'll show you how to work it. Use the limit comparison test to determine if the series converges or diverges, and we have this ugly little series here. Okay, what to compare it to? That is the hardest thing for students to pick. I just always say, look at the numerator, look at the denominator, determine who's running the show. So in the numerator, who's running the show? 4 rad n. Do you want to keep the 4? You can keep the 4. I'm not going to. Basically, rad n is running the show in the numerator. Rad n is n to the 1/2. Who's running the show in the denominator? The 10n to the 3/2, or basically n to the 3/2. It's the highest power. The highest power term runs the show. Okay. Clean that up. N to the 1/2 over n to the 3/2, that's 1 over n. Well, what do we know about the sum? N equals 1 to infinity of 1 over n. That's the harmonic series. It diverges. Okay, so now let's see. I suspect my series will diverge also. So let's take the limit as n goes to infinity of the terms of our series over 1 over n, the harmonic series. Okay, so if I'm dividing by 1 over n, that's the same as multiplying by n over 1. So we have the limit n goes to infinity. If I multiply by n over 1, now I have 4n to the 3/2 in the numerator over 10n to the 3/2 minus 7n plus 2. And then to take this limit, divide by highest power of n in the denominator, which is n to the 3/2. All right, so then now we have the limit as n goes to infinity. In the top, we just have a 4. In the bottom, we've got a 10 minus n over n to the 3/2. That's going to be 7 over n to the 1/2 plus 2 over n to the 3/2. All right. And then if n's going to infinity, then 7 over n to the 1/2, that's going to 0. So is this. So I'm just left with 4 over 10, which is 2/5. I don't care what this number is, just so long as it's less than infinity, it's a finite number, and it's not equal to 0. Great. What does that tell me? That my series does the same thing as the series I compared it to. Who did I compare it to? The harmonic series, who diverges, which means my series diverges also. Okay, so then the sum, n equals 1 to infinity, 4 rad n over 10n to the 3/2 minus 7n plus 2. They behave the same, so it also diverges by limit comparison test. Okay? Couple problems that happen. If this limit comes out to infinity or 0, the test is inconclusive. Usually that's because you picked the wrong thing to compare it to. If you had picked 1 over n squared, then it would have gone to infinity, and then you would have had, I'm pretty sure, yeah. And, you know, then the limit comparison test would not have been applied correctly. It doesn't give you any information. It means you picked the wrong thing. All right, so just keep that in mind. And then your series does the same thing as whatever you compared it to. So in another case, this could be converges if we compared it to something that was convergent. All right, just keep that straight. It could tell you either thing. And like I said, I have a whole video on it if you want more examples. That's enough though. Next test, alternating series test. This one's a favorite. You use it anytime you have an alternating series. So if you see -1 raised to the n, or n minus 1 or n plus 1, that part doesn't matter. But if you just have like -1 raised to n and some stuff, then it's time to bust out the AST. So we call, you know, the original terms an, right? Like an would be -1 to the n minus 1 bn. So when you strip away the alternating part, what's left over we refer to as bn. You could also think of it as absolute value of an. Same thing. The two conditions for AST are that bn has to be decreasing. bn plus 1 less than or equal to bn means it's decreasing. Also, the limit as n goes to infinity of bn needs to be 0. If both those are satisfied, then the alternating series is convergent. If one of these conditions fails, then the AST fails, and then usually you just use test for divergence to show the series diverges. Okay, let's look at an example or two. So determine the convergence or divergence of the alternating series. So first let's identify bn. bn is natural log of 6n plus 3 over 6n plus 2. So the first thing I need to show is bn is decreasing. So bn plus 1, let's see, that would be ln of 6 times n plus 1 plus 3 over 6 times n plus 1 plus 2. And I can already tell I'm having problems. I don't know if it's greater than or less than bn. It's not obvious. So when it's not obvious, it feels like, ooh, it's probably derivative time. So let's let f of x, always switch to x, equal ln of 6x plus 3 over 6x plus 2. And before I take the derivative, I'm going to use my log properties to make it easier. So ln 6x plus 3 minus ln 6x plus 2. So what's f prime? So derivative of ln of 6x plus 3, that's going to be 6 over 6x plus 3 minus, this is 6 over 6x plus 2. You could probably already tell this is going to be negative because this denominator is bigger, so this whole thing is smaller than this term. But if that's not obvious, that's okay. Just get a common denominator. So I'd multiply this by 6x plus 2, and then this by 6x plus 3. So then what do we got? We got 36x plus 12 minus 36x minus 18. Over 6x plus 3, 6x plus 2. And these 36x's cancel. And then I just have negative 6 over 6x plus 3 and 6x plus 2. And now remember, we're only plugging in values for x that correspond with the original series where n varies from 1 to infinity. So these x's are only going to go from 1 to infinity. So I can tell the denominator is always positive, and then the numerator's negative. So the derivative is less than 0. What do we know if the derivative's less than 0? That means f is decreasing. Woo. Which means Bn is decreasing. Holy smokes. Okay. Second thing I have to check is the limit as n goes to infinity of Bn should be 0. So here's Bn. I know there's that ln. You can pass the limit through. We have a theorem that tells us you can take the limit of a composition of functions as long as it's continuous. So here we've got limit, n goes to infinity now, 6n plus 3 over 6n plus 2. And I think easiest thing is just, divide by n, top and bottom. And let's see what happens. We've got ln, limit, n goes to infinity. This is 6 plus 3 over n over 6 plus 2 over n. Okay. 3 over n and 2 over n are going to go to 0. So we just have 6 over 6. That's 1. So this limit's going to be natural log of 1, which is 0. Phew. So both conditions were satisfied. So that means the original sum, n equals 1 to infinity of negative 1 to the n, natural log 6n plus 3 over 6n plus 2 converges by alternating series test. And I love a good abbreviation acronym situation. So there we go. Okay. AST. Use it when you have an alternating series. Here's one. Great. We have the sum, n equals 1 to infinity of negative 1 to the n times 3n plus 3 times n to the 8th plus 1 over 4n cubed plus 6. So this stuff is Bn. Bn is 3n to the 8th plus 1 over 4n cubed plus 6. Now, you don't need to check both conditions in order necessarily. If you already can tell, like one's going to fail, do it first. And I can already tell the limit as n goes to infinity, the second condition of Bn is not going to be 0. How do I know that? Because look, the degree of the numerator is higher than the degree of the denominator, yeah? So if I divide by highest power in the bottom, which is n cubed, this is limit, n goes to infinity. This is 3n to the 5th plus 1 over n cubed over 4 plus 6 over n cubed. So look what happens. As n goes to infinity, yeah, that goes to 0, and that goes to 0. But 3n to the 5th is going to infinity. Divided by 4, it's still going to infinity. So this is infinity, which is not 0. So it fails AST, which means that the series is divergent. Now, based on how picky your teacher is, they may still want you to use the test for divergence to finish off the problem. So just check with them. If usually they let you stop here and just say the series is divergent, then cool. Fast forward through the next 30 seconds. But if not, what you would do is you would just say, okay, since these terms aren't going to 0, they're going to infinity, and the original series was alternating, that means all of the odd terms, okay, like A1, A3, A5, A7, those would all have negative 1 raised to an odd power. So those would be negative terms. So they're approaching negative infinity. And then the even terms are the ones that are approaching positive infinity, which means the limit as n goes to infinity of the original negative 1 to the n, 3n to the 8th plus 1 over 4n cubed plus 6, that limit does not exist because it's bouncing around the odd terms. It's basically like this. Let me give you a little graph. So pretend this is an, and then this is n. So what's happening is like the odd terms are going to infinity and they're negative. There's the first term, second term, third term, fourth term, fifth, like this, see? They're approaching infinity and they're bouncing away from each other. That's what's going on. So you could say the original sum, n equals 1 to infinity of this thing. I don't feel like rewriting it. Woo. We can say that it diverges by test for divergence. And that's like a super proper answer. A lot of teachers, though, will just let you stop here. If it fails AST, you can say it diverges. So I wanted to show you both cases because I don't know who your instructor is, how picky they are. Okay. All right. Now, let's talk about testing for absolute and conditional convergence. We say a series converges absolutely if the sum n equals 1 to infinity of the absolute value of an converges. We say a series converges conditionally if it does not converge absolutely, but the original converges without the absolute value. And this next theorem is very helpful. If a series converges absolutely, then that means it converges conditionally. So absolute convergence is the strongest kind of convergence. If the sum of the absolute value of the terms converges, then obviously the original would converge as well. Conditional convergence means the absolute value, the sum of those terms diverges, but the original converges. And I have a whole separate video on this topic. Basically, you always want to check for absolute convergence first, because if the series passes, then you're done. If the series doesn't converge absolutely, then you do AST to check for conditional convergence. And I have a very snazzy little flow chart to walk you through the whole process. I highly suggest you check it out. I'll link it right here. Okay. So determine if the series converges absolutely. Just converges is the same as converges conditionally or diverges. So I'm going to check for absolute convergence first. Test for absolute convergence. All right, so I'm going to look at the absolute value of an, and all that does is get rid of this alternating part. Okay, so we're going to have 3n to the 4th plus 6 over 8n to the 6th plus 9. So do I think this series is going to converge or diverge, and what test should I use? That's the tricky part. So I'm looking at the numerator. Who is running the show? That 3n to the 4th. Look at the denominator. Who is running the show? The 8n to the 6th. N to the 4th over n to the 6th reduces to 1 over n squared. And we know the sum, n equals 1 to infinity, of 1 over n squared. That's a p series, and that converges because p equals 2. So I have a feeling my series should converge also. How can I show it? Perfect test to use is limit comparison test. So let's look at the limit as n goes to infinity of 3n to the 4th plus 6 over 8n to the 6th plus 9 over 1 over n squared. So that's going to be the limit. N goes to infinity. If I divide by 1 over n squared, that's the same as multiplying by n squared over 1. And then that's going to distribute. So we have 3n to the 6th, plus 6n squared over 8n to the 6th plus 9. And then now to take this limit, let's divide by highest power of n from the denominator. So that's n to the 6th. And then now let's see, this is the limit as n goes to infinity. In the numerator, we're going to have 3 plus 6 over n to the 4th. And then in the bottom, 8 plus 9 over n to the 6th. So I can tell, all right, these two guys are going to go to 0, and I'm just left with 3/8. What test did I just use? Limit comparison. All that I care is that this is finite and not 0. And that tells me that my series does the same thing as the one that I compared it to. Who did I compare it to? Oh, this cute little convergent p series. Fabulous. So that tells me the sum, n equals 1 to infinity, of absolute value of an, which is 3n to the 4th plus 6 over 8n to the 6th plus 9, converges by, tell the people what test you used, limit comparison test. Okay, that means that the original series converges absolutely because even without the alternating part, it converged. So then I can say the original, n equals 1 to infinity, of negative 1 to the n, 3n to the 4th plus 6 over 8n to the 6th plus 9 converges absolutely. And we're done. Now here's the mistake a lot of students make. They would look at this and just get so excited and do AST. And that's cute because that would tell you it converges conditionally, but then you still didn't check if it converges absolutely. And to do that, you'd have to go through this whole process, okay? If you do this whole process first and it passes, then you're done and you can skip AST. AST only will answer the question of conditional convergence, right? Because it's for alternating series. It cannot tell you if a series converges absolutely. So don't do it first. I know it's exciting. I know it's a nice test, but please resist, okay? Great. I mean, this is a tricky idea, so let's do another one. Yes. Here we have the sum, n equals 1 to infinity, negative 1 to the n, over 9n to the 1/4 plus 1. Again, we're going to see if it converges absolutely, conditionally, or diverges. I know it's tempting, but please don't do AST first. All right. So let's test for absolute convergence first. This is one of the hardest ideas, okay? So don't feel bad if you're like, oh. Absolute value of an, absolute value of the original, just gets rid of that negative 1 to the n, right? So it's just going to be now 1 over 9n to the 1/4 plus 1. Okay, what do you think this guy's going to do? Who's running the show in the top? There's nobody in the top. It's just a 1. Who's running the show in the bottom? N to the 1/4. What do you know about this sum? N equals 1 to infinity, 1 over n to the 1/4. Oh, it's a P series. Yes, it is. P is 1/4, which is less than 1. So this P series diverges. I suspect then that the sum of the absolute value of an will diverge also. Let's use limit comparison test to check. So limit n goes to infinity of 1 over 9n to the 1/4 plus 1 over 1 over n to the 1/4. So that's the same as multiplying by n to the 1/4 over 1. That's going to be the limit. N goes to infinity, n to the 1/4 over 9n to the 1/4 plus 1. I'm sorry that thing keeps popping up. It's because I'm left-handed, and when I write, I have to like rest the side of my hand, and I try not to, but I know it's annoying. I'm so sorry. To write neatly, though, I have to semi-rest it. Okay, n to the 1/4, divide highest power of n in the bottom, and then let's see what we got. So we have limit n goes to infinity, and then in the top, we're just going to have a 1. In the denominator, that's going to be 9 plus 1 over n to the 1/4. 1 over n to the 1/4 goes to 0. So we're just left with 1/9, which is finite and not 0. So what does that tell me? My series does the same thing as the one that I compared it to, which means the sum n equals 1 to infinity of the absolute value of an, right? So just 1 over 9n to the 1/4 plus 1. It also diverges by limit comparison test. So that means the original, what was the original? The sum n equals 1 to infinity, negative 1 to the n over 9n to the 1/4 plus 1 does not converge absolutely. So sad. But does it converge conditionally? It could. So now we can test for conditional convergence. Anytime you test for conditional convergence, you use AST. That's the only test. Got it? After you test for absolute, if it fails, then you do conditional convergence with AST. There's no other test to use. So Bn is the same as absolute value of An, 1 over 9n to the 1/4 plus 1. We have two conditions to check. First, Bn plus 1, is it less than or equal to Bn? Is it decreasing? Oh my, I need more room. Hold up. Okay, this one we can just use an inequality because only the denominator will change. When I plug in n plus 1, right? Only the bottom's changing. And I can say for sure this is bigger than the original denominator. Yes, that's clear. So then Bn plus 1 has to be less than or equal to Bn. Perfect. And then second condition I need to check is the limit as n goes to infinity of Bn, 1 over 9n to the 1/4 plus 1 goes to 0, which it does. This denominator is going to infinity. So this whole thing's going to 0. Woo! So then that tells me that the sum, n equals 1 to infinity, negative 1 to the n, over 9n to the 1/4 plus 1, converges by AST, which tells me that the original series, to answer the question, converges conditionally. The absolute value of the terms, that series diverges, but if you leave it alone and use the original as an alternating series, it converges. That means it converges conditionally. On the condition that it's an alternating series, to be precise. All right, that was good. There's more cases. If you need more, I got more. You just got to watch another video. Okay, ratio test. Woo, I love the ratio test. So fun. A lot of the time you use the ratio test when you see factorials. The exclamation points. It doesn't mean you yell in math. It means something else. Okay, so given the sum n equals 1 to infinity of an, if the limit as n goes to infinity of the absolute value of an plus 1 over an is less than 1, then the sum of an converges absolutely. If that limit's greater than 1, the sum of an diverges. And if the limit is 1, that means the ratio test fails and you get no information and you have to use a different test. Okay, so usually that happens if you use the ratio test when you shouldn't. Pick a different test. Probably you should have done like limit comparison test or integral test or something like that. Like you're just too gung-ho on the ratio test. Okay, here we go. So use the ratio test to determine if the series converges or diverges. The trickiest part is being good at cleaning up the factorials. So here we go. Let's look at the limit as n goes to infinity. And the cool thing is actually it always tells you when the series converges, it'll converge absolutely. And if it diverges, it just straight up diverges. There's no chance for conditional convergence with the ratio test, which I like. Black and white. Okay, so we need the limit as n goes to infinity of absolute value of an plus 1 over an. I don't see any alternating stuff. There's like no negative 1 to the n's in there, so I don't need the absolute value. But just remember, it's supposed to be there originally. Okay, an plus 1 is going to be 5 times n plus 1 factorial squared. Yes, don't be scared. Over 2 times n plus 1 factorial. Divided by an, so I'm going to just already multiply by the reciprocal, so 2n factorial over 5 times n factorial squared. Okay, clean it up. So we've got the limit, n goes to infinity, This is going to be 5 times, I'm going to write it as n plus 1 factorial, n plus 1 factorial, because it's squared, right? And I know it's scary to square factorial, so just separate them. No big deal. Be careful here. This is 2 times n plus 1 factorial. That 2 distributes. So this is actually 2n plus 2 factorial down here. And then 2n factorial up here. And then 5. And then I'm going to, again, separate the n factorial squared into n factorial times n factorial. Right off the bat, I can see these 5s are going to cancel. And then you got to know how to break down the factorials to help them cancel as well. So always start breaking down the one that's bigger. So what do I mean by that? N plus 1, these are bigger than n, so I'm going to break those down. And just start expanding them until you hit the factorial that's in the opposite side of the expression. So n plus 1 factorial is n plus 1 times n factorial. And I've got 2 of those. Okay. And then 2n plus 2 factorial in the bottom there, that's 2n plus 2 times 2n plus 1 times, I'm going to stop now, 2n factorial, because I see a 2n factorial in the numerator on the other term. And then now I'm ready to have a little cancel party. This is just my favorite part. Watch this. Bam! Bam! Goodbye. You too. Farewell. So long. Okay. Now we just got to take the limit of the survivors. So this is limit, n goes to infinity, n plus 1 over 2n plus 2. You know what that is? That is 2 times n plus 1. And then I've got 2n plus 1. This cancels with this. My God, the cancel party continues. Then we have limit, n goes to infinity, n plus 1 over 4n plus 2. Divide by highest power of n, which is n to the first. Okay, okay. So this is limit, n goes to infinity, 1 plus 1 over n over 4 plus 2 over n. This goes to 0, this goes to 0, and at long last, I have my limit, which is 1/4, which is less than 1. So that means the original series, n equals 1 to infinity, 5 times n factorial squared over 2n factorial converges absolutely by the ratio test. Woohoo! Actually, I put this on the final this year. I think almost everybody got it right. Okay, here's another one. Ooh, do you want to pause the video, try it on your own? You should. Check if you actually know what's going on. Or are you just being entertained? That's fine too. I would say though, if you have to actually take a test soon, you need to practice on your own, you know. Watching me is like watching professional sports. It's entertaining, it looks easy, but it doesn't mean that when you try to do it, you'll be any good. So I say, give it a pause, try it on your own. You can handle it. Are you ready? Okay, here we go. Trying to see if okay, let's hop to it. So we have limit, n goes to infinity, absolute value, -1 to the n plus 1, n plus 1 factorial squared, 8 to the n plus 1, over 2 times n plus 1 factorial, divided by the original, which is times reciprocal of the original, which is -1 to the n factorial squared, 8 to the n, and then 2n plus 1 factorial here. Okay, since I have these absolute values, -1 to whatever, doesn't matter, is gone, right? It's going to make everything positive. And so I'm just going to dump those and then stop writing the absolute value, since now I'm just left with n's and we're good. Again, I have n plus 1 factorial squared, so I'm going to break it up like I did in the last problem. That's n plus 1 times n factorial times n plus 1 times n factorial. Now 8 to the n plus 1 is 8 to the n times 8 to the first. And then this down here, this is 2n plus 2 plus 1. So it's 2n plus 3 factorial. So that's 2n plus 3, 2n plus 2, 2n plus 1 factorial. I stopped there because I already could see, ooh, there's 2n plus 1 factorial. So now it'll cancel. And then here's n factorial, and 8 to the n. Now my favorite part, cancel party time. Yes. So the 8 to the n is gone. So is 2n plus 1 factorial. So are these n factorials. Goodbye. Who survived the massacre? An n plus 1, an n plus 1, an 8, a 2n plus 3, and a 2n plus 2. Okay. Survivors, gather round. Limit, n goes to infinity. I'm going to put the 8 in the front, and then we have n plus 1, n plus 1. In the bottom, I have 2n plus 3, and then 2n plus 2 is 2 times n plus 1. Cancel, cancel. I can cancel the 2 and the 8. Now this is a 4. Yes. So we have limit, n goes to infinity, 4n plus 4 over 2n plus 3. I can already tell this is going to go to 2 if I just look at the ratio of the leading coefficients, but if your teacher's a stickler, here we go, dividing by n. So now we have limit, n goes to infinity. In the top, that's just going to be 4 plus 4 over n, and then in the bottom, 2 plus 3 over n. And then these both go to 0, and we're just left with 4 over 2, which is 2. And what do I care about that number? Ooh, it's bigger than 1, which tells me my original series, the sum, n equals 1 to infinity, negative 1 to the n factorial squared times 8n over 2n plus 1 factorial diverges by ratio test. And you don't do AST. No, no, no. If you've used ratio test, there's no chance for conditional convergence. If it does not converge absolutely, it diverges. Whoops. If it's inconclusive, then that means you picked the wrong test. So pick a different test, then who knows? But as long as you get a conclusion, it's just one or the other. All right. The less popular, ugly younger brother of the ratio test is the root test. No, I'm kidding. The root test, it's nice. I don't find it as fun for some reason, but maybe that's just me. So given the sum of an, if the limit as n goes to infinity of the nth root of the absolute value of an is less than 1, then that means the sum of an converges absolutely. If that limit's greater than 1, then the sum of an diverges. And then again, if the limit's 1, then the root test fails. Fails means it's inconclusive. It doesn't give you any information. You need to pick a different test. All right. So again, like maybe you should have done limit comparison test, or maybe you should have done, that's probably the only one that would work if you're being desperate. Okay. So let's see here. They tell me in the directions, use the root test. If they didn't, how would I know? Because everything's kind of raised to the nth power in the bottom, you see. If you try to do ratio, this n to the 1 over n that's in the bottom would make life pretty nasty. So that's why that's not a good idea. All right. Just trying to see if I've worked this problem out earlier somewhere, and I can't find it. But it's fine because I know how to do it. But all right, let's go. Very bizarre. Okay, so we have the limit. You take the nth root of everything, okay? The limit as n goes to infinity of the nth root of absolute value of n over, this is n to the 1 over n plus 10 to the n, and absolute value. Now, taking the nth root of something is the same as raising it to the 1 over n. So this is the same as the limit as n goes to infinity of n to the 1 over n over, and then since this is already being raised to the n, it cancels out. So you have n to the 1 over n, that looks ugly, plus 10. Okay, how to take this limit? Because look, what's going on with n to the 1 over n? As n goes to infinity, this base is going to infinity, and the exponent is going to 0. And infinity to the 0 is an indeterminate form. So we have to do L'Hopital's rule. But we only can use L'Hopital's rule on functions that are differentiable. Oh me, oh my. And we have a sequence n to the 1 over n. That is not differentiable. So you go, let f of x or y be x to the 1 over x. Then ln of y equals ln of x to the 1 over x, which equals 1 over x times ln of x. And then now the limit as x goes to infinity of ln of x times 1 over x is the same as ln of x over x, right? That's infinity over infinity. So we can use L'Hopital's rule. So that's the limit. X goes to infinity, derivative of the top over derivative of the bottom. This goes to 0. But remember, we added in an extra ln. So the original limit without the ln of x to the 1 over x is e raised to that, which is 1. Oh. So what does that tell me? We know that the limit as n to the 1 over n also goes to 1. So this is 1 over 1 plus 10, which is 1/11, which is less than 1. Whew! Okay. So that means the original series, n equals 1 to infinity, n over n to the 1 over n plus 10 to the n, converges by root test. A lot of the time when you apply the root test, you're going to see this n to the 1 over n pop up, and you do need to take that limit, work through it off to the side using L'Hopital's rule and change it to f of x. Don't say infinity to the 0 is 1. That is total illegal garbage. That's not always the case. I know in this particular problem, this did come out to be 1, but that is not the right way to think about it, okay? Okay, good. Glad we had that talk. Now we're going to talk about finding the interval of convergence of a series. And anytime you're asked to find an interval or radius of convergence, you need to do ratio test. Always and forever. That means it's ratio test time. And now we have x's in here, so we have to find which x's are on the interval or radius of convergence that allows this infinite series to converge. Great. So here we go. We're going to look at the limit as n goes to infinity. Again, absolute value of an plus 1 over an. So you always do this when they ask you to find interval or radius of convergence. So this is going to be limit n goes to infinity, absolute value, an plus 1, that's going to be x minus 9 to the n plus 1 over 9 plus 8 times n plus 1, divided by an is times 9 plus 8 over n over x minus 9 to the n. Okay, so let's see, this is the limit, n goes to infinity, absolute value, x minus 9 to the n times x minus 9 to the first, over, this is going to be what? 8n plus 8 plus 9, so 8n plus 17 times 8n plus 9 over x minus 9 to the n. And then now I can cancel out this x minus 9 to the n, right? And here's the interesting part. So the limit is as n goes to infinity. So this x minus 9 in the absolute value is not changing as n goes to infinity. So you can take it out of the limit, all right? Just keep the absolute value because I don't know, x could be positive, x could be negative. N is going to infinity. I know n is positive, but I don't know about x. So keep those absolute values on there. So you got absolute value, x minus 9 outside, okay? Then limit n goes to infinity, 8n plus 9. You don't need absolute value on these. I know n is going to infinity. It's not negative. Okay, you could divide by n to the first, or I'm very over it. 8 divided by 8, this is going to 1. So I just have absolute value of x minus 9 times 1. Now, I just did the ratio test, right? I said you always do ratio test. And I know that my series will converge so long as this limit is strictly less than 1. So that means we need the absolute value of x minus 9 to be less than 1. That means, if you remember how to solve absolute value inequalities, x minus 9 has to be less than 1 and greater than negative 1. Add 9 to get x by itself, like this. And then you have 8 is less than x is less than 10. So the radius of convergence, ROC, is 1. It's this number right here. It's 1. Now, x has to be between 8 and 10, and it is centered at 9. Centered at 9 because, see how it's x minus 9? So it's always x minus c, where it's centered, is less than a. That's the ROC. And then it's centered at c. So basically what it looks like is here's 9, here's 8, here's 10. This is a 1. That's why we say the radius of convergence is 1. Now I need to test the endpoints to see if x equals 8 and x equals 10 can be included in the radius of convergence, because I have basically 4 options. My interval of convergence could be 8 to 10 like this. It could include 8 and not 10. It could include both, or it could include 10 and not 8. So which one is it? You have to do a test for each of the endpoints. Which test? Whichever's appropriate. So let's go back to the original right here. And then you're gonna plug in 8, and then you're gonna plug in 10 and test, okay? So let's plug in 8 first. Oh, I need so much more space. Why did I think 1 page would be enough? No, no, no. Okay, let's check x equals 8. So then we have the sum, n equals 1 to infinity. You guys, I forgot what it was. Hold on. Okay, so you have 8 minus 9 to the n over, it was 9 plus 8n. Okay, okay. So this is the sum, n equals 1 to infinity. 8 minus 9, that's negative 1 to the n over 9 plus 8n. Well, this is an alternating series, so let's use AST. What's Bn? Bn is everything without that negative 1 to the n. So it's just 1 over 9 plus 8n. So can I show Bn is decreasing? Yeah, Bn plus 1 is 1 over 9 plus 8 times n plus 1. So since the denominator is getting bigger, of course, that's less than the original. Perfect. And then the second condition is that the limit as n goes to infinity of Bn needs to be 0. Is that true? Oh yeah, denominator is going to infinity, so this is 0 for sure. So then that means the sum, n equals 1 to infinity, negative 1 to the n over 9 plus 8n converges by AST. So that means x equals 8 belongs to the interval of convergence. So here's how you write it in math language. Are you ready? That means x equals 8 is an element of the interval of convergence. Ooh. Okay, so what does that tell me? 8 is included. Yeah? So it's not this one, and it's not this one. Now I just got to check, is 10 included? So I know which of those two it is. So let's check with x equals 10. These are tedious when they ask for the full interval of convergence. If they just wanted the radius of convergence, we'd be done. We know it's 1. Okay, so now I'm going to plug in a 10 here instead. So 10 minus 9 to the n 10 minus 9 to the n over 9 plus 8n. So this is just the sum, n equals 1 to infinity. 1 to the n is just 1, okay? Over 9 plus 8n. Ooh, who does this remind you of? It's reminding me of 1 over n. The sum of 1 over n is the harmonic series. What do I know about the harmonic series? It diverges. So I feel like this is going to diverge as well. If I were to use direct comparison, I'd have to show that the terms of this series are bigger than those of the harmonic series, which is not true actually. They're a wee bit smaller, but it's still going to diverge. So if you can't do direct comparison, that's when you do good old limit comparison test. So we're going to use LCT. You can't just say, hey, I feel like it's going to diverge because it reminds me of harmonic. That's cute what you feel, but you have to use a test, okay? Use that intuition and pick a test. So we have 1 over 9 plus 8n divided by 1 over n is the same as times n over 1. So then we have limit, n goes to infinity, n over 9 plus 8n. Divide by highest power of n in the bottom, which is just n to the first. So then this is the limit as n goes to infinity of 1 over 9 over n plus 8. So as n goes to infinity, this goes to 0. I'm just left with 1/8. Remember, all I care when I do limit comparison test is that this limit is finite and not 0. And then that means both series do the same thing. So my series does the same thing as the harmonic, which diverges. So then that means the sum, n equals 1 to infinity of 1 over 9 plus 8n also diverges. And I wanted to see if 10 belonged to the interval of convergence. Well, it surely does not. So how do you write that in math language? You could say that means x equals 10. Oops. X equals 10 is not an element of the interval of convergence. So the interval of convergence includes 8, but not 10. So in interval notation, it's like this. Ooh, that was so spicy. That's a long problem. I wanted to show you like the worst case. Okay, here's a cute one. Why do I say it's cute? You'll see. So again, we're finding the interval of convergence. Always use ratio test. Okay, guys? I know students love when I say always statements. Like, is that always going to be? Yes. If you have to find radius of convergence, interval of convergence, use ratio test. So here we go. We're going to look at the limit. N goes to infinity. Absolute value, an plus 1. So that's x minus 6 to the n plus 1. Over, ooh, be careful with the parentheses, please, 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 please. And then divided by the original is times reciprocal of the original. Okay, good. Now let's break it down so we can have a cancel party. So this is limit, n goes to infinity, absolute value. This is x minus 6 to the n, x minus 6 to the first, over. Now this is 2n plus 2 factorial, right? So if I break that down to cancel, that's 2n plus 2, 2n plus 1, and then 2n factorial. And then we have over here 2n factorial over x minus 6 to the n. Good. So now cancel party can commence. X minus 6 to the n cancels. 2n factorial cancels. And then remember, this is a limit as n goes to infinity. So in this limit, x minus 6 is not changing, it's a constant. Remember though, x could be any real number. So I'm going to keep the absolute value, take it outside the limit so I can just concentrate on the key players, right? And then we have limit, n goes to infinity. Oh shoot, now there's just a 1 in the top over 2n plus 2 times 2n plus 1. So this denominator is going to infinity. 1 over infinity is going to go to 0. This whole thing's going to 0. So what does that mean? I'm left with absolute value of x minus 6 times 0, which is 0. And I just did the ratio test, guys. All I care is that this limit is less than 1, and 0 is always less than 1, no matter what I plug in for x. So that tells me the radius of convergence is infinity. Any real number I can plug in for x, and the interval of convergence is all real numbers from -infinity to infinity. I don't have any endpoints to test. I have no other work to do. That's why I told you you'd love this one. So radius is infinity. Interval is -infinity to infinity, and we're done. Mic drop, pencil drop, whatever you want to say. Woohoo! I love these ones. And I'll put them on the test sometimes because, you know, you don't need to do long problems all the time. It's not fun. All right. Hang in there. We're almost done. I'm getting tired and I'm hungry, but we're going to finish this off. So representations of functions as power series. We manipulate geometric series to represent certain types of functions. So remember, geometric series, you could start at 1, you could start at 0. That'll switch up from time to time. But the OG, n equals 0 to infinity of r to the n, or x to the n, when you take the infinite sum, it's 1 over 1 minus x, based on this finding a sum of an infinite geometric series. That is like your building block. That is your bread and butter. So if you have some other kind of series, like the functions that we're going to look at later, you want to see how you can relate them to 1 over 1 minus x. Now, sometimes it just takes a little bit of like manipulation with addition and multiplying and stuff like that. I'm not going to do any of those basic cases. I have a whole extra video if you want to watch. I'm just going to do 2 spicy little examples that are probably test worthy, okay? So here it says find a power series representation for f of x, and f of x is 1 over 1 minus 6x squared. And you might say, okay, it's reminding me of this guy. Just make this a 6. So you would make that a 6 and then square it, right? Wrong. Please do not square an infinite series in this course. It doesn't work out well. I've tried so many times in my career. It's never worked out. There's always a different way to do it that comes out better, okay? So the answer is not to square a series. Anytime the degree is a 2, a 3, or whatever, you're going to start with the original 1 over 1 minus, in this case, 6x, and then we're going to differentiate to get that power higher. Okay, so start off with no exponent in the bottom. Start off with what feels nice, 1 over 1 minus 6x. Can you write a power series for this function? Why, yes, I can. It's going to be the sum, n equals 0 to infinity. Instead of x to the n, I'm going to have 6x to the n. And then I can write that as the sum, n equals 0 to infinity of 6 to the n times x to the n. Okay, now at the moment, this is raised to the first, and I would love it to be squared. So to get it to go up a degree, we're going to take a derivative. 1 over 1 minus 6x is the same as 1 minus 6x to the negative first, yes? Yes. Okay, so this is the sum, n equals 0 to infinity, 6 to the n times x to the n. Let's take the derivative with respect to x of both sides. Okay. On the left-hand side, we now have, bring that power down in the front, -1, 1 minus 6x to the negative second, and then don't forget the chain rule. Derivative of the inside is -6. How do you differentiate an infinite series? It's not too hard. One thing to keep in mind is the index needs to change. When we start at n equals 0, that corresponds with x to the 0, which is 1. The derivative of a constant is 0. So when you take the derivative, this is gone, and now you have to start at n equals 1. You do this anytime you differentiate, and the first term is a constant. That's probably the trickiest part. That's it. Watch out. Those are my watch out eyes. So you still go n equals 1 to infinity. We're taking the derivative with respect to x, so 6 to the n is just a constant. How do you take the derivative of x to the n? You bring the exponent down in the front, and then you subtract 1. Okay, we took the derivative, look, and we survived. Tell about it. Let's clean this up. This is going to be positive 6 over 1 minus 6x squared, and then that's the sum. N equals 1 to infinity, 6 to the n times x to the n minus 1. Okay, now let's see. What do I have? this looks good. I wanted a power series for this f of x. What's different about them? I got the squared in the bottom. Woohoo, go me. However, I need a 1 in the top, and I currently have a 6. So let's get rid of it. Let's multiply by 1/6. And then here I will also multiply by 1/6. So then now I have 1 over 1 minus 6x squared equals the sum, n equals 1 to infinity. Watch this. 6 to the n over 6 is 6 to the n minus 1. Yes, it is. Times n times x to the n minus 1. This is my f of x. If possible, you usually want to have x to the n in your final answer. So I need to add 1, which means I need to start my sum at 0 instead. So if you start 1 lower, you bump up everybody by 1. So you'd have 6 to the n times n plus 1 times x to the n. And you guys, I'm going through all of these really quick because this is a review video, okay? I'm not breaking down every little thing the way I do in the lecture videos because this is for the sake of review, all right? The purpose of this is you're cramming for your final, so here I am. But it's not, if you need more explanation, then watch the lecture videos. All right, that's it. Great. Next one, f of x equals x squared times natural log of 1 plus 4x. I put this on the final this year as extra credit. Yeah, I do. I do put an extra credit problem on there on occasion. Just give them a little wiggle room, for that grade. All right. Now, the trick with the ln's is always the same. You take their derivative and then play around with them. So, here we go. First things first, I'm just going to say I know what I'm going to do. I'm going to say let g of x equal ln of 1 plus 4x. G prime of x, please take the derivative. Anytime you have an ln, you need to take a derivative. So the derivative of ln of 1 plus 4x is going to be 1 over 1 plus 4x times 4 by the chain rule. Can you write a power series for this guy? Oh yeah, I can, because remember, it's 4 over 1 minus negative 4x. So that's 4 times the sum, n equals 0 to infinity, negative 4x to the n. So that means g prime of x equals 4 times the sum, n equals 0 to infinity. Break up that negative 4x to the n. It's negative 1 to the n, 4 to the n, x to the n, which is, now bring that little 4 inside. He's so lonely. So now we have 4 to the n plus 1, x to the n. This is g prime. Well, nobody cares about g prime. I want the original. I want g of x. So g of x, how do you undo a derivative? You integrate. So I need the integral, n equals 0 to infinity, negative 1 to the n, 4 to the n plus 1, x to the n dx. Don't have a panic attack. Everybody except x is a constant. So when you integrate, nothing changes. Leave this alone. Just rewrite it all. Oh, so relaxing. How do you integrate x to the n? You add 1 to the exponent, and then you divide by the new exponent, and then you have a plus c. How do you find c? In this case, this is centered at 0, so I'm just going to plug in 0 for x. So g of 0 is going to be the sum. If x is 0, every single term is 0. And what was g of 0? Who was g of x? G of x is ln of 1 plus 4x. So g of 0 is ln of 1 plus 0, which is ln of 1, which is 0. So this all equals 0. So c is 0. Great. So g of x is this sum here. And I can clean it all up. Let's just make these n's and start at 1 instead. That means I'm going to subtract 1, and then this will be n minus 1. So this is the sum, n equals 1 to infinity, negative 1 to the n minus 1, 4 to the n, x to the n over n. And this was who? This was ln 1 plus 4x, right? Yes. Is that what I want? No. F of x has an extra x squared. F of x is x squared times g of x. Okay, then multiply this by x squared. Okay, so then now f of x is the sum n equals 1 to infinity, negative 1 to the n minus 1, 4 to the n, x to the n plus 2 over n. Now I know I said usually you want this to start at n, so you could shift it, but then this would be n minus 2, this would be n minus 2. I don't know if it's going to look any better. I would just leave it. Ask your instructor if they care. Just do whatever will get you full credit, okay? Good. I have a whole video on differentiation and integration of power series, so if you need more examples, watch them. Last idea, Taylor and Maclaurin series. So theorem tells us if f has a power series representation at E, meaning f of x can be written as the sum n equals 0 to infinity of Cn times x minus a to the n, that's a Taylor series, with radius of convergence r, then those coefficients Cn are the nth derivative at a divided by n factorial. Just memorize that. A different form of writing the Taylor series is just expanding it. So here, this is what you have up above, right here. Hold on. Don't freak out. Don't freak out. That's the same as this. And then if you were to like list out the terms, then that's what you have right here. This is for n equals 0. This is n equals 1, n equals 2, etc. Maclaurin series is just a special case of Taylor series when a is 0, when the series is centered at 0. That's it. So if you know the formula for Taylor series, you know the one for Maclaurin. All right, so let's look here, a couple examples. Find the Maclaurin series for the given function using the definition. Definition is what's right here. So I like to make a little table to organize everything, to find the coefficient Cn, okay? So this is the function, this is f of x, and I always make the table like this. So you have n, you have your nth derivative at x, and then you have your nth derivative at a. In this case, since it's a Maclaurin series, a is 0, so nth derivative at 0. Okay, how many derivatives do you take? However many you need to find a pattern. So I'll do 0, 1, 2, 3, 4, 5, I don't know. So the 0th derivative is just the original function. What's the derivative of 9 or sine 9x? It would be 9 cosine 9x. Second derivative, negative 9 squared sine 9x. Third derivative, negative 9 cubed cosine 9x. Fourth derivative, positive 9 to the 4th sine 9x, etc., etc. And then 9 to the 5th cosine 9x. I'm not like expanding, 9 squared, 9 cubed, so I can see the pattern more easily. Now let's plug in 0 for x. So sine of 9 times 0, that's sine of 0, that's 0. Cosine of 0 is 1, so this is 9. This is 0. Negative 9 cubed. This is 0. 9 to the 5th, etc. So let's see if we can notice a pattern. What I have so far are just the nth derivatives at a. I have to divide each of them by n factorial to get these coefficients. So here we go. So sine of 9x, let's do the n equals 0 term. Well, it's just gone. Plus n equals 1. You're going to have the nth derivative at 0 times x minus 0 to the first over 1 factorial. So this is n equals 0, this is n equals 1, n equals 2 is 0, n equals 3, we have negative 9 cubed times x cubed over 3 factorial. N equals 4 is 0, n equals 5 is 9 to the 5th, x to the 5th over 5 factorial. And then hopefully you can see a pattern by now. If you can't, then just keep going in the table till you do. So what do I notice? Well, the even terms are gone, right? They're all zeros. Only the odd terms remain. I have 9 raised to odd powers. I have also x raised to odd powers, and I have odd factorials in the bottom. Plus, it's alternating. Positive, negative, positive. The 7th term would be negative. So let's see how we can write this in sigma notation. I'm going to start at 0. And I need 9 raised to an odd power. Odd powers are going to be 2n plus 1. So let's see, 9 to the 2n plus 1. Yep, if n is 0, I'll have 9 to the first. X has the same exponent. And then you have that same odd number factorial in the bottom. And then it's alternating, so I'm just going to have negative 1 to the n. And that should work, yeah. Because if n is 0, this is positive. So the first term works out. And then if you plug in n equals 1, then we're at this term, okay? So in the series, this corresponds with n equals 0. This corresponds with n equals 1. This corresponds with n equals 2 when we write it here, okay? Because the even ones all canceled out. All right, good, that's it. That's a Maclaurin series using the definition. Let's do a Taylor series with the definition. This time we're centered at 3. Okay, so same table. So you have n, the nth derivative at x, and then the nth derivative at a, which in this case is 3. How many do you need? However many till you see a pattern. I only needed 3. 0, 1, 2, 3. Okay, so original function, then one derivative would be 8e to the 8x. 2 derivatives, 8 squared. 3 derivatives, 8 cubed, etc. That's pretty easy. Now plug in 3 for x. So this is e to the 24, then 8e to the 24, 8 squared e to the 24, 8 cubed e to the 24. Okay, I feel pretty good about the pattern, don't you? So f of x, let's start with the 0th term. You'd have e to the 24 times x to the 0 over 0 factorial. Next term, 8e to the 24, x to the first over 1 factorial. Then 8, oh my God, my left-handedness, 8 squared, e to the 24, x squared over 2 factorial. 8 cubed, e to the 24th, x cubed over 3 factorial plus blah, blah, blah. So then now nothing's canceling out like the last one, right? You're not having only odd terms, only even terms. And it's pretty straightforward. So we have the sum n equals 0 to infinity. Everybody has an e to the 24th and it's not changing. So just keep e to the 24th in there. Then notice, like this is 8 to the first. We didn't have an 8 here. Technically, there's an 8 to the 0. So you have 8 to the n. Hold on, it's an ugly 8. 8 to the n. You also have x to the n. And then you have n factorial in the bottom. Oh my God, you guys. I messed up. This should be x minus 3. You can tell I'm getting tired, huh? Okay. To the 0, x minus 3 to the first, because it's centered at 3. Please forgive me. So then this is x minus 3 to the n. Okay. We didn't have that in the last one because it was centered at 0. I think I did write it on the first one, then I was like over it. Yeah, these are all technically like x minus 0 cubed. X minus 0 to the 5th. So you don't see it in the Maclaurin series, but here for the Taylor series, since it's centered at 3, you see it. Okay, that's that. At least we caught it now. Good. All right, now, some Maclaurin series are very famous, so I recommend you memorize these. I talk about different tricks for how to memorize them. I just always remember like sine is an odd function, so its Maclaurin series representation has all odd powers, factorials. Cosine's an even function, hence evenness. Tan inverse looks like sine, just no factorial. Blah, blah, blah. E to the x is adding sine and cosine together, just not alternating. And then 1 over 1 minus x, you should know. This is binomial series. I don't know. I don't make my students learn that. And then here's ln of 1 plus x. You can memorize it or just derive it like we did earlier. So a couple things you could do. Why it would be good to memorize these. Like, look at the pattern here. Find the sum of the series. I told you in the very beginning of the video, perhaps you've forgotten, the only time we can find sums of series are if they're geometric, telescoping, or a Maclaurin series. So this is a Maclaurin series, and I can recognize the pattern. This is the sum, n equals 0 to infinity. It's 2 to the 2n plus 1 over 3 to the 2n plus 1, 2n plus 1 factorial. Ooh, and it's alternating, isn't it? So let me add in there a negative 1 to the n. Well, which Maclaurin series does this look like? It looks like sine of x. It looks like the sum, watch this, n equals 0 to infinity, negative 1 to the n. I can write this as 2/3 to the 2n plus 1 over 2n plus 1 factorial, yeah? And then can you see? That's basically like this right here. It's just x is 2/3. So the sum of this series is sine of x, which is sine of 2/3. Boom, done. Cool, huh? I love those ones. Next one, you can also use series to evaluate limits. You can also use Maclaurin series to integrate. So here what we're going to do is use the Maclaurin series representation for e to the negative 5x to evaluate this limit. So e to the negative 5x, did you forget what it was? It's okay, I'll show you. So here, you're just going to replace x with 5x this time, okay? And it's negative, oh, it was negative 5x, wasn't it? Yeah. Okay, so this is going to be the sum, n equals 0 to infinity. Negative 5x to the n, that's going to make it negative 1 to the n, 5 to the n, x to the n, over n factorial. So let's just list out the first few terms. If n is 0, first term's going to be 1. If n is 1, you have minus 5x plus 5 squared x squared over 2 factorial minus 5 cubed x cubed over 3 factorial plus blah, blah, blah. So now let's plop that into the numerator of our limit, you see? So instead of writing e to the negative 5x, I'm going to write all of this with the dot, dot, dot. Oh, yeah. 1 minus 5x plus 5 squared x squared over 2 factorial minus 5 cubed x cubed over 3 factorial plus blah, blah, blah. And then you still have all this goodness. So write minus 1 plus 5x over x squared. All right, usually like some cutesy little cancellation will happen here. So the 1 cancels, the 5x cancels, and then let's see what we're left with. Limit x goes to 0, 5 squared x squared over 2 factorial minus 5 cubed x cubed over 3 factorial plus blah, 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 over x squared. I'm going to divide everybody by x squared separately. And then look what happens. The x squared cancels in this term. So now I have limit x goes to 0 of 5 squared over 2 factorial minus 5 cubed. I still have 1x left over 3 factorial plus, this would be 5 to the 4th, x to the 4th, which would reduce to x squared over 4 factorial minus blah, blah, blah. And if x is going to 0, this would go to 0, this would go to 0, so does everybody else, except for this little lone soldier. And that's our limit, 25 over 2. Ba-dum-bum. Okay, I think that was all I got. Yeah. I'm sorry if it felt rushed. I wanted it to just be a review video, not take 10 hours of watch time. But obviously these concepts are very in-depth, tricky, whatnot. So like I keep saying, go back, watch the full-length video lectures if you just need to fill in some gaps on any particular topics, okay? But hopefully this was helpful if you just wanted like a quick little brush up of everything and then just kind of go dig deeper on the stuff you need before your final, you know? And if you made it this far, leave me a comment. I'd love to hear your thoughts. And I hope you guys all do great on your finals. Have a great summer. I love you all. Thanks for your support. Give the video a thumbs up. Subscribe if you haven't already. And I'll talk to you guys soon. Bye.